So I'd like to spend the next few minutes telling you a little bit about the Andlinger Center and some of the logistics about this meeting. The Andlinger Center, as many of you may know, was established in July of 2008, thanks to an extraordinary gift from Princeton alumnus and international business leader Gerhard Andlinger. The center has three core areas of research. So we would like the center to support a vibrant research and teaching program with a focus on three things: developing new alternative energy sources, improving the efficiency of devices that consume and generate energy today, and inventing and improving carbon capture and storage techniques that will enhance our ability to reduce the amount of CO2 entering the atmosphere. So these are three broad themes. The center aims at pursuing these studies closely with scientists and policy analysts across the university. And this is very important, with an eye towards translating fundamental knowledge into practical solutions. This is built into the core mission of the center. We envision the center to be located in what we call a neighborhood, energy and environment neighborhood, which will comprise the E-wing of the engineering school, Bowen Hall, which is where the Prism Center stands, and the Carfield Center, which will move across the street, whereas we intend to have a very nice conference center in that location associated with the Andlinger Center. And there will be, very importantly, a state-of-the-art facility. A major theme will be, within the center, will be to bring together the finest minds in energy and environmental science with those who work on new materials. This was a strategic choice that Princeton made to capitalize on an existing strength. For example, to develop flexible solar panels or to develop heat resistance coatings that will enable power plants to operate more efficiently. And you're going to hear about both of these themes today. So accordingly, the new center will host a state-of-the-art facility, a shared facility that will have state-of-the-art imaging and nanofabrication facilities in addition to individual investigator labs. Because of the focus on translating fundamental knowledge into practical solutions, close interactions with industry will be, from day one, fundamental to the existence of the center. And planning for the new building therefore includes space for industrial collaboration laboratories, as well as for hosting industrial visitors for extended periods of time. We selected the architects in January, Todd Williams and Bill Itzine, a New York-based firm, and we're in the middle of the design process for the center. The search committee has identified a candidate for the director of the center, and we're now in the middle of negotiations, trying to attract this person to Princeton. So we're very excited. We're sort of in the quiet but very active phase. A lot of things are happening. Speaking about the director, in going with the theme of the importance of industrial contacts, the director will consult with two external advisory boards. One will be focused on scientific issues and will be primarily but not exclusively academic. And the other board will be focused on strategic and policy concerns and will be mostly composed of people from industry. In addition, the director will oversee the recruiting of new faculty to the center, will oversee the development of the energy and environment neighborhood, provide leadership of research, educational, and outreach activities, and also, very importantly, allocate a non-trivial amount of funds for innovative research internally at Princeton. So today's meeting is the first of what we hope to be many meetings. And when we thought about the format, of course, we didn't know what sort of response we would get. We got a very good response. And so we have to cram everyone into just 10 minutes. So the format will be talks. We have 2 coffee breaks and a reception for people to mingle and follow up. We want the industrialists to hear about the exciting research going on here and programs that exist, and we want the academics to hear about the needs and interests in industry, and hopefully the 2 coffee breaks and the reception will allow for plenty of opportunity for people to talk. If time allows and we're doing okay with the timing, right before the reception we'll also have a little bit of open discussion. But if you don't have enough of structured discussion, please be proactive. Contact the faculty members, or the faculty members contact the industrial members whose presentations you're interested in, and be aware that this is just the first of many forums that we intend to organize. This is all I wanted to say, so it gives me great pleasure to introduce Greg Olson, who is my partner in crime in organizing this. Greg is a lecturer in the Electrical Engineering Department, and of course is president and founder of GHO Ventures. Jeff?
Thank you. As Pablo mentioned, I'm entrepreneur in residence here. One of my functions is to meet with faculty and students about ideas for starting new companies or spinning off technologies. And I've enjoyed that part of my being here. But let me start off with what I see the purpose of this meeting is. First of all, does this make sense? Now to me it makes a lot of sense, but I'd rather hear that from you than my own thoughts. Give you an opportunity to see what faculty are working on here. Faculty can see what the local companies are doing. It's a lot better to meet and interact and have coffee, and we have a reception afterwards rather than just read about stuff in newspapers and trade journals. And of course is to determine what the next steps are. How do we go forward from here? So after this meeting we'll kind of make some notes, distribute them, and go to Plan B. A little bit of history. Princeton's had a number of really successful industrial academic interactions. And I just put 3 of them up here, but there are many more. These are the ones I've been involved with. About 20 years ago, there was a POEM, Center for Photonics and Optoelectronic Materials. Jim Sturm was heavily involved in creating that. PRISM, that sort of morphed into Princeton, which combined materials with the optoelectronics. And then finally, most recently, we have MIRTH with Prof. Claire Gamakel, and I'm not going to steal her thunder. I'll let her tell you about it, but that's also been a very successful industrial interaction. Just to give you my personal interaction, my history with Princeton and these types of academic interactions. I've had 2 startup companies, one Epitax in 1984, and the second one is called Sensors Unlimited. Epitax was more fiber optics, Sensors Unlimited was fiber optics and also infrared imaging. I got involved with Steve Forrest, who was on the faculty. He joined in 1992. About the same time, Marshall Cohen and I started Sensors Unlimited. And it was really a synergistic thing. And POEM, which was then the Industrial Affiliates Center, really provided the nucleus for us to interact. Steve was coming in. He needed to set up his equipment, get his students going. We were starting a company. We had engineers, but we didn't have a lot of equipment and facilities. So via joint R&D programs, we were able to share these things, and both really benefited from them. Lots of student jobs, not only summer jobs. I think at Census we probably hired maybe close to 10 Princeton graduates. We licensed patents. It was just a really nice interaction. Between these 2 companies, net, there was over $1 billion in sale. Over 1,000 jobs were created. And one of the best part is we were able to pay back over $100 million to the government in the form of corporate and payroll taxes. So it was really a win-win-win for everybody. And I give a lot of the credit for both of these companies to the centers that existed at Princeton University. So what I'm trying to do is to tell you it's really worked for me, and it can work for you too by getting involved with the university. As I said, it's been a great deal for everybody. Again, the MIRTH Center, I'm going to let Prof. Gamakel tell you more about that. But they've attracted companies from all over the United States that participate in it. In fact, I was down at a trade show called Clio last week in Baltimore, and I see they had their own booth at a trade show. So, it's really been an active organization, and really gets out and interacts with the world. Now, if I was an industrial member, if I hadn't been involved in these things, I might say, well, how can a university help me? And, just a couple, I think you're going to find out by listening to these talks. But I think one of the best ways is by joint funding programs. My companies have used the SBIR system, Small Business Innovation Research. It's a funding system the government has for small businesses. But now with the stimulus program, there's a lot of other things going on with the Department of Energy, most recently these ARPA-E programs, but there are going to be more as the stimulus stuff evolves. And many, many of these programs either encourage or require companies to interact, to have universities on their programs, and vice versa, for universities to go out and find industrial participation. So I think the stimulus program is, just one of many ways that this can interact. At first glance, nanotechnologies and lasers, what does that have to do with me? Well, that may sound a little foreign to you or a little bit up in the clouds, but when you get into pollution monitoring and gas sensing, then it's not so far removed, because I think a lot of you deal with things like that. Let's turn it around. How can companies help universities? Just make them aware of the problems you have. An outlet for technology. There's a lot of great technology here, and if you get to talk to the people, this is how you'll find out. I can tell you from my own experience, Princeton's very easy to work with. John Ritter, in terms of licensing, he's a deal maker. And you won't sit there for tens of meetings. You'll get to the point, and we've worked with him for over 20 years, and we found not just John, but the whole university to be really easy and friendly to work with. So I think that's the end of my comments. I think next on the schedule is supposed to be the funding lady, Paula Durand. I don't see her here yet, so I think what we'll do is maybe start on, if you don't mind starting a little early, Claire, get on with that part of it, and when Paula comes in, we'll just have her talk about the funding programs available for the state.
All right. Thanks for the introduction, Pablo. So I want to take the time and for 10 minutes tell you something about MIRTH. MIRTH is an NSF-sponsored engineering research center. It's a consortium of 6 universities. Princeton is the lead. We have about 40 faculty, 100 plus students year-round, 140 students in the summer. And what the center is doing, it takes a technology that's just coming out of the research labs and tries to push it out into the real world. And to do that, it works very closely with industry. And the technology that we are pushing out into the real world is mid-infrared, laser-based trace gas sensing. So it's anything that's related with having a gas sample and wanting to know what chemicals are in there at very small quantities, parts per billion, parts per trillion sensitivity. So examples that come to mind: air pollution, urban air quality, indoor air quality, but also sensing for long-term air pollution. It is what amount of carbon is human-generated, which one is just natural carbon. Think about cap and trade, for example. So it's sensing of chemicals. It's also, if you switch from pollution and environmental to medical, it's breath analysis. If I breathe out, my breath has all kinds of chemicals in there. If I can detect them, I can diagnose, monitor disease, and so on. It's also process control. It's automotive control. So it's sensing of chemicals. And if you look at the sensor market, it's huge, right? There are plenty of sensors. But essentially, it falls into a couple categories. There are those that are cheap. That's your carbon monoxide sensor. It's cheap, easy to install. Everyone knows how to use it, but it's not sensitive enough. And then you have the other part of sensors that are wonderful sensors, sensitive enough, but they need a PhD to operate. They're expensive, they're bulky. You couldn't afford more than a few of them. So what's missing is a very high-end sensing technology, parts per billion technology, at a consumer product level. We have a new technology. It's semiconductor-based spectroscopy. And being semiconductor-based, it should sit on the same curve as other semiconductor-based materials on a Moore curve. The more you need, the cheaper they get. So the ultimate goal is a small, tiny, cell phone-sized sensor that measures chemicals, vapors at very small quantities. Right. So we build little things, right? Sensors. How do we do that? It's an interdisciplinary, cross-disciplinary research effort where we combine the expertise of climate scientists. This is aerosols above Princeton on a sunny day. Medical expertise, breath analysis, with electrical engineering. This is a wireless module. It has all the electronics to run the system, detect the system on it. We talk about components. This is actually a gas sensing cell. It's about this tiny. And components, laser research. And why does it work? Well, if you think of trace gases, in the mid-infrared wavelength range, they have color. They have unique colors. And so if we can make lasers that match the colors of trace gases, we can detect them by absorption. So here's an example for ammonia. In the mid-infrared wavelength range, it has the strongest absorption lines, the strongest optical features. And so that's where we want to catch the trace gas and detect it. Just to make the point, different trace gases, they're all important ones. Each one looks different and very characteristic in that wavelength range. And so we have projects, 40 faculty, 100+ students need a lot of projects to work on that are urban air quality sensing, regional climate, breath analysis, homeland security applications. It's sensor systems. It's point sensors, measuring a gas sample here and now. It is remote sensors, integrating over a couple hundred meters, integrating over a kilometer to match climate models, for example. It's sensor networks. Sensor networks is coming up very strongly. And then the little components that go into those systems that build the whole thing. Research. That was the research we are doing. A center such as ours has two more pillars. So it's the research, and then it has education and industry outreach. Here are our education programs. They're more lively if you put pictures to it. But essentially, we graduate students who are better trained because they're more cross-disciplinary trained. They have visited more than just one university. Many of them take internships in industry. Many take international internships. So they're pretty much, they're very well versed in collaborating, in interacting with a variety of people when they graduate. And then, as Greg already mentioned, Greg Olson already mentioned, we work with industry. We have an active industry collaboration program where we provide membership at various different levels, where we provide services at various different levels, and we receive feedback, input, but also monetary cash contributions. And here's the list of our current members, and you see that it's small businesses, large businesses. 70% of our industry members are in fact small business and startup. And since our inception, Mirth in 2006, we have not lost a single company. We've only been growing in number of companies that we work with. All right, if I have 2-3 more minutes left, I thought I should tell you something about the technology we are doing. And we're doing a lot of things. So I pick one thing. And the one thing I picked is our field campaign last summer at the Olympic Games in Beijing, where we brought 2 instruments to do trace gas sensing and a group of environmental weather pollution forecasting modeling people. Right? So the pollution forecasting folks were part of the local team of scientists that provides feedback to the International Olympic Committee about pollution and the games. Right, so why did we go to Beijing, and why am I showing you this? First of all, it is to be part of something real. And so sometimes universities are accused of not being really part of the real world. I want to show you that we are part of the real world. We can get, especially engineers, we can get out there, our student groups, and be part of something where it matters. And Olympic Games do matter. So being part of something important. Next thing, it's a unique time series experiment in terms of civil and environmental engineering. That's extremely recent too. The question is, can a community influence on the short term its air quality? Right? Could New York City improve its air quality if it would put in congestion pricing? How do you do that experiment? That would be a very hard experiment to do. Here, we had a wonderful experiment because factories were shut down, car traffic was diminished to odd, even day driving, trucks, traffic was diminished. And the question is, can you actually clean up the air? And the answer is yes, it works really well. And finally, we wanted to test our equipment. And so we had actually 3 ammonia, carbon dioxide, and ozone that we were after because you can measure them and they look very characteristic in the mid-infrared. And so we measured those trace gases with our experimental equipment. And the system's about this big. Well, it was an open path system where it sends out a laser beam 75 meters, beam comes back, and we measure along this beam path. It was about 2 miles from the main Olympic sites. We also compared it with the official instruments. And you go there and you see the official instruments, they're all from US companies, and there's a big box that measures ozone, and then there's a big box that measures ammonia, and then there's a somewhat smaller box that measures CO2. And our box is about as big, but it can measure everything. All right, here's the example. This is ozone, day-night cycle, and our instruments does as well or better as the other instruments. All right, but just to show, we took out 10 students, some faculty, we all had fun, but we also were part of something important. And so as a professor here, working with industry is another opportunity to be part of something real and something important. So we listen to you, what are important problems that need good solutions. And I think we're ready to help work on these things. Thank you.
Thank you.
Excellent. Okay. I apologize for that. Thank you so much for having me here. Thank you, Pablo, for the introduction. My name is Craig Arnold. I'm in the Department of Mechanical and Aerospace Engineering, and also with Princeton Institute for Science and Technology and Materials. And today I want to tell you just a little bit about the kinds of things we do in my group related to energy storage, particularly things related to how we can optimize electrochemical energy storage devices. Think of things like batteries or capacitors and such like that. And what we're going to do is we're going to try to meet some of these challenges by understanding the nanostructures, how we can optimize them, understanding the mechanics and how that relates to the electrochemistry, and also doing some advanced laser processing type approaches to see how we can further optimize these systems. First off, my group, as well as the funding agencies, particularly I want to thank Elena and Christina, 2 of my students who are doing much of the work I'm talking about here. Now, clearly energy storage is important. I don't need to give you a full background on this. You can think of a variety of reasons why you care. A car, an iPhone, wind power, all of these things, right? If it's wind or solar, the wind isn't always blowing or the sun's not always shining. There we go, good. So you need to worry about how you might load level these types of systems. In other cases, you might think of having a need for extra energy. In the case of the iPhone or a car or something, you might think of something being portable. And finally, perhaps most importantly, is that novel systems require novel solutions. And you know, the constant question I get is, well, can you just make a single battery? Can you make some magic system that will solve all of our energy needs? And the answer is, well, it's not that simple, because each particular system has particular demands that we have to meet. And so one has to look at different things, such as, should the battery be flexible? Does it need long life or lightweight, or other types of metrics that you care about? And so clearly energy storage is one of the key challenges we faced in the 21st century. But also, you might think of, say, semiconductor or electronics, and we think of something like Moore's Law, where the storage capacity in a computer doubles every 18 months. Well, unfortunately for batteries, that doesn't quite work In the case of batteries, the doubling time is about 60 years. So clearly something's up here. What's going on? Why does it take so long? And well, the answer is that the chemistries haven't changed much, but the way we understand these systems and the way we apply these systems to other types of devices start becoming very important. Now, in particular, in my group, we focus on three main areas in energy storage: batteries, supercapacitors, as well as some recent work looking at how we can integrate systems and build up larger things. And some of the particular topics are listed here, but the key thing that I want you to take home from these different areas in our group is that with respect to batteries, we care about making batteries small. We care about making them long-lasting so that you can have many, many cycles that go into them. And we care about advanced applications. Again, thinking about things like flexible platforms or very small micro batteries, things like that. And in just very briefly in the next couple slides, I'll talk about two of these things. I'll talk about the relationship between mechanical and electrochemical properties, as well as some advanced laser processing and embedding of microbatteries. In the case of supercapacitors, what you can think about is the way we try to control the nanoscale structures. We try to optimize the size scale of these materials. We try to reach very high powers, make these systems faster. And again, we look to novel applications. How can we implement small-scale ultracapacitors, maybe flexible ultracapacitors, things like that. And finally, on integration systems, we look at questions like how do we integrate storage with alternative energy? How would you put a battery with a windmill or a wind turbine? What type of battery do you need? And also hybrid types of systems for small-scale applications. And in the case of supercapacitors, I'll just very briefly talk about these two topics on optimizing the architecture, as well as, again, some advanced laser processing. So let's start off on batteries in this lightning-quick tour of electrochemical energy storage. 2 minutes here, right? There's a real common misunderstanding about batteries. People think that they fail because the chemistry dies or the battery gets used up or things like that. But when you're talking about rechargeable batteries, the typical mode of failure is actually mechanical in nature. You can think of the laptop batteries that were blowing up, a little while back. That's clearly a mechanical failure. But you might think of a flexible battery where you bend it, maybe some kind of fiber. But this is also true in fixed batteries. And the way to understand that is that lithium batteries, the ions have to intercalate into the host lattice. What that means is that large ions have to squeeze themselves in between the planes of atoms that are already there. And so, for instance, you might have ions coming in. Once they combine with their electron, this whole thing grows just a little bit. Now, this could be a tremendous amount of strain on the systems, on the order of 7 to 10%. It doesn't sound like a lot, but that's enough to destroy most materials. And so it's actually critical to understand the relationship between the mechanics in these systems and how that affects the electrochemistry. And this ultimately can lead to improved lifetime. So if we can stop the system from failing mechanically, we could get this system to last longer. And so the type of experiment you might think about, you might think of a flexible battery, but as I said, traditional batteries as well. And the kind of thing we do is we might squeeze these things. We might press on them a little bit, and we might see how they respond. Understand some of the electrochemical and mechanical interactions. So for instance, you might think of mechanical terms like fatigue or stress or strain. But if we put that into the battery terminology, we're really looking at the cycle life. We're looking at the energy density or the power density in these types of systems. So that's sort of topic one, main area. In the case of laser processing on these systems, when you start throwing lasers into the mix, you can start doing all sorts of novel types of changes to the materials in the system. And one particular thing that I want to talk about is a laser direct write embedding approach. And again, there's a lot of details here, but really all you need to keep in mind is that what we can do is we can use a laser to modify a surface where we want to put a battery. We can drill a hole or something. We can then print a battery directly in that hole and cover it up so you couldn't even see the battery after the fact. And so here's a picture of it over here. This is the subject of a recent patent of ours. And you can see here's a dime, here's a picture of the battery. If you look at it on the side, you might have an anode, a cathode, all embedded within a substrate. So you wouldn't even see the thing, very small. Here's some other general pictures. But in general, when you start throwing laser printing methods into the electrochemistry, you can start actually making real systems, real devices that have significant amount of energy density as well as power density per unit area. So small-scale applications, once again, novel types of implementations of energy storage. Okay, so that's the quick bit on batteries, the quick thing on supercapacitors. Many of you might not know what a supercapacitor is. Basically, you could think of a supercapacitor as kind of like a battery and kind of like a capacitor. Okay? It's very fast like a capacitor. It can give up its energy very rapidly, but it can store a lot of energy just like a battery. And basically, the way it works is you have a really high surface area. If you put a lot of surface area, you have a lot of place for these chemical reactions to occur. And there's various different types of flavors, details. But in general, one of the things that you're really striving for in these systems is how can I engineer a material that has a very high active surface area that I can somehow process into an appropriate device that I'm interested in. And so, supercapacitors have a number of advantages over batteries. This was a slide I put together for an animal tracking symposium. But basically, they have a greater cycle life. They can cycle many, many times. They have very high power. They're very good at charging and discharging. But they have a relatively low energy density compared to batteries. They have a shorter shelf life. So in general, the way to think of these systems is to think of a Ragone chart like this. And so you might think of fuel cells as being very high in energy but low in power. Capacitors are somewhere in the middle. And so we play all sorts of games with these systems trying to make them better, trying to make them more useful in various types of applications. So for instance, one of the things we do is we look at optimizing the nanostructure. How can you make more surface area for a given material? So for instance, we might use carbon nanotubes or other types of nanostructured materials. And I'm just about out of time, right? I'm long past out of time. Oh, okay. I could speak even faster.
I would be closer to you.
He's standing. He's getting when he starts pulling me off of here, right? We could again deal with these nanostructures. We can deal with various types of situations related to these things. The last thing I want to leave you with, and it really is the last thing I promise, is again how you can further increase your ability to process these materials when you start using lasers. You can start playing some real neat tricks. For instance, I can actually create a capacitor using 2 lasers to basically modify the material in such a way that the end result is I have a capacitor left behind. And so all of that aside, let me just conclude with leaving this slide up here to tell you a little bit about the kinds of things we do. And thank you for listening to my rambling here. And I'll be around and we can chat later if anyone has interest.
I'm really speaking not just for myself, but for Professor Ju, who's in the back of the audience here, and Professor Law, and Professor Sokolow, all of whom are part of the Thermal Sciences group in Mechanical and Aerospace Engineering. Let's see if I can. I want to emphasize the issue that we're most interested in is the idea of trying to reduce carbon emissions in net cycle over the next period of time. And you can see that we're talking about reductions here that are in the order of very large numbers in comparison to present CO emissions. In particular, the issue of transport and carbon emissions from transportation systems are thought to be one of the most difficult areas to deal with. And it's partly because of the size of the amount of energy that's being fluxed through the transportation system, as well as its source, which is principally petroleum. As such, we have to worry about backward compatibility for very large amounts of capital investment in terms of transportation systems, and also forward design issues. As we look at those issues, we can see that we want to keep some compatibility with the existing processing issues of petroleum. And what I want to emphasize is 2 points here. One is as we go from Saudi Arabian petroleum to the kinds of things we'll be using for petroleum in the future, the amount of energy processing requirement becomes very severe, principally because of hydrogen content in these fuels and the hydrogen upgrading necessary to shift the amount of hydrogen in the system towards what we want to use in real systems. This introduces a whole series of areas for producing hydrogen that are very important, but I think everyone now agrees that biomass is going to be a key to addressing these climate issues. The difficulty is that if we look at all of the renewable resources, including biomass, those numbers do not compare well with the total amount of energy production that we really require. For us as well, we have a very large amount of coal that's being used in electricity, and we know that China is going to increase its use in this area as well. So how do we deal with this? Well, there's at least two ways to process biomass. This is representative of one. I grow materials that have very high oil content. I extract the oil. I process the oil. And now you'll notice no oxygen in these systems. These are not the typical kinds of ethanol things that you and I are used to. They are now fully hydrocarbon compatible with petroleum products, as you see here on the left. I want to note one other thing here that's very important. These are the kinds of properties that are used to define what I put in a jet engine. If I go to a gasoline station and I collect gasoline today, tomorrow it's not the same. Next December, it's not the same at all. And if I do that in Asia or I do that here, it's very different. The question is how do I integrate these alternative fuels into those kind of problems? And this is why I need very strong compatibility. Now, why is this important? Because in comparison to kerosene derived from petroleum, this is the use CO2 emission that would have come from burning petroleum. But if I use any of these other oils, that use CO2 emission is replaced by the fact I photosynthetically captured the CO2 from the atmosphere. The problem is, each one of these oils represents only about 40% of the mass of the biomaterial I grew, and the biomaterial that I'm using is very resource limited. So the amount of fuel replacement that I can get is very limited this way. Can I use it better another way? This is the other way. Not only can I use it better, but I can also develop ways of using coal. You've all seen the clean coal ads recently. It really is clean. The idea is to use photosynthetic sequestration of CO2 from the atmosphere to displace the CO2 that's going to be present in the fuel when it is burned. I'm going to combine it with coal. I'm going to generate a liquid fuel. I'm going to simultaneously generate electricity. So I'm replacing both the electrical generation market and the transportation fuel market simultaneously. The co-production of fuels and power turn out to achieve extremely good optimal economics with very good solutions of many of the environmental problems. Important here is that I can also eliminate very large amounts of the nanoparticle emissions that occur from pulverized coal firing by replacing it with gasification as the means of making my gasified streams. In order to do synthetic fuel conversion, I need to remove sulfur, so I end up with very low sulfur fuels this way. In addition, I'm going to process some of the synthetic gases to power right on site. And you'll notice I've got two routes to that, one this way, one that way, that I can also use liquid fuels with it. This is to balance the two processes. So oxygen firing of such a gasification system also produces a CO2 stream, which is very pure in its process, can be dried easily, can be compressed, and can be carbon sequestered and stored. That's the key to this technology. How big of an advantage is this? As I showed you here, we got about an 85% reduction in C emissions. If I do this purely with biomass in this problem, bio to liquids plus electricity, I get a minus 22% carbon reduction in comparison to petroleum. If I do this with 38% biomass with coal, I get a 0 net carbon cycle out of this process. I'd be happy to share more about the economics of this. This comes from an analysis with my colleagues, Bob Williams, Eric Larson, and the Princeton Environmental Institute here. So you can see that if I use one of these processes of CBTL, coal plus biomass to liquids with full recycle, carbon capture and storage, or once through, I can generate very good economic solutions to this problem. Turns out not the one that produces most liquid fuel is the best. This is. It's called systems analysis. I need to know a lot about heat rejection in these systems and its quality to pick that one. Okay, well, now what's the problem? This all looks very simple. The problem is this is what the molecular weight distribution looks like in any of the fuels we use for transportation. And we don't know how all of those little molecular weight distributions change every time I make an alternative fuel. I need to find ways of compatibility between alternative fuels and petroleum so I don't disrupt the distribution or storage or utility in any of these systems. So these are the questions that need to be answered, and these are the questions that the Thermal Sciences Group are addressing. We have a number of projects, and I'll try to keep everybody online here. We have a project called the Carbon Mitigation Initiative that's directed out of PEI, which Steve Picala and Rob Sokolow are the PIs. It's funded by BP and Ford. We have a next generation aircraft fuel project looking specifically at this problem for aircraft fuels and for producing very low net carbon emissions and particulates. That's PI'd by me and involves the people you'll note here all at Princeton. We have a Air Force MURI program which involves a number of other institutions and PEI as well. And we are looking at how to model real fuels with what are called surrogate mixtures of small numbers of molecules. A similar program involves Professor Law. That's stationed on the West Coast, PI'd by Professor Agapopoulos at USC. You'll notice another set of industries, and you'll note who's funding this. Air Force is a big player in this area. And finally, we have hydrogen combustion in gas turbines. This is an issue with the syngas power generation problem and controlling emissions. We've been working with Nettle and also Siemens. And finally, just recently, we have gotten an Energy Frontiers Research Center award from Basic Energy Sciences, which Emily will tell you a little bit more about. So this gives you a kind of a broad picture of what thermal sciences is involved in here. We work on the fire safety aspects of this, on the fuel property aspects, and you'll notice the kinds of things you're talking about in terms of real-time sensing are very important for control of these kinds of systems. Thank you.
So, welcome everyone. I'm going to tell you about, just very briefly, about a variety of projects that are going on in my group. I'm a theorist. What we do is we start with the basic physical laws, namely quantum mechanics, to understand how atoms interact both in molecules and materials. And very recently, in the last couple of years, I've just decided that almost everything I do now, I want it to be related to this topic here. Okay, so I'm going to lead you through that. In particular, I'm going to have a couple of slides that talk about this issue that Fred introduced, which is the issues associated with combustion. You know, I think that in many ways, when people talk about new energy technologies, they often stop and say, combustion, well, it sounds like a dirty word. The fact is that as Fred pointed out, combustion is going to be with us for a very long time. It's not something we have any choice about. We absolutely need to find ways to optimize engines and the molecules that make up the fuels in order to do this in such a way that we're burning more cleanly and also capturing the CO2, et cetera, all the things that Fred said, in addition to hopefully dealing with issues of our own national security by deriving our sources of fuels right here at home. So I have a project now that is part of this larger center that I have a couple of slides I'll tell you about. This center was the only center that was funded in the area of combustion in the entire nation. So we're very proud of that fact. We think we put together, I should say, Ed Law really put together a dream team, at least that's what the reviewers said, so I can say that, of people to work on this problem. And so I'll talk more about that very briefly. Pablo mentioned, I've been working for over a dozen years now looking at materials issues associated with the extreme conditions inside jet engines. In particular, these jet engines are not only used to power aircraft, of course, but they're also used in stationary power plants, different size modules, obviously. But the materials issues are precisely the same. What you see on, there is somewhere a pointer, but I don't see it. So I should have taken yours, Lynn.
It's right in your slide.
That's okay. 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 So how did I miss it? Okay. Oh, I see. No, that's all right. Anyway, so so what we've been doing is to try to understand the issues associated with how you protect these metal jet engine blades that operate actually at temperatures above their melting point. That should frighten all of you. That you all take airplane trips, right? And these things are subject to the flame temperatures in these engines actually are above the melting point of the metal alloy that's used for these jet engine blades. How does that work? It works because they're protected by a ceramic coating, a very, very interesting ceramic coating. And we have been involved, multi-layer ceramic coating, we've been involved in understanding how to improve that coating so that one can operate at even higher temperatures and improve the fuel efficiency or improve thrust if that's your goal. For flying. Okay, another area that was recently funded, we've done a little bit of work related to this. This is a very nice picture of the experimental fusion reactor that is going up in Europe that the Princeton Plasma Physics Lab has been involved in. They inspired me to start thinking about some of the materials issues associated with containing the fusion plasma. There are really important issues, as you can imagine. The temperatures get very high. There are neutron fluxes that come out of the fusion plasma, such that we need to understand, and there's also the particular issue they're worried about that they asked me to think about has to do with tritium, which is a hydrogen isotope, getting into the metal that faces the plasma. So I'll talk about that very briefly. Another area that I won't talk about at all, I'll give you an example of what we do in this area and in this area, and the rest of it I'm not going to talk much about limits in the limited time available, but if you're interested, we can talk about it separately. Wally Soballejo, I stole this picture from him. He works on lightweight vehicles. I also work on lightweight vehicles. We're interested in developing metal alloys, aluminum and magnesium alloys that can be used for lightweight cars, for any vehicle you like, ships, airplanes, cars, etc. Obviously, that will improve their fuel efficiency. Another Energy Frontier Research Center that was just funded by the Department of Energy that I'm involved in, and also my colleague Miko Hataja is involved in, is looking at new materials for solid oxide fuel cells. The internal combustion engine is an incredibly efficient way of processing fuel. But another way that it has tremendous promise for generating electricity is by taking fuels and actually running them through a cell like this that actually has the potential to be able to use dirty fuels even without problems. And so this is another mechanism for generating electricity, either from hydrogen or from hydrocarbons. And then lastly, I'll just say that I just found out that another Department of Energy grant that I had pending was funded to develop new materials for photovoltaics, so for solar cells. And I have another one pending having to do with essentially doing what's called photocatalysis, which is to take sunlight and make liquid fuels. And hopefully that's going to get funded too. So these are all the areas that we're working in. And now I'll just spend a minute telling you, this slide is from one of my now collaborators, because he is part of the Energy Frontier Research Center. Bill Green at MIT put together this slide to just point out things that I don't even need to discuss in detail because Fred did such a good job already. But the point is we have to start thinking about a whole bunch of new fuels that are going to be coming online and how they operate, both understanding how to optimize their combustion chemistry and the fluid dynamics involved in the mixing of the chemistry and the thermodynamics with the fluid, with the gas, and how to then take that information to understand how to design new engines. There are a lot of new engine technologies that are being considered. They all have quite different regimes in terms of pressure and temperature that one needs to think about. And so this was the motivation really to go to the Department of Energy, Basic Energy Sciences, and say, we want to put together a team that goes all the way from molecules, which is where I live, all the way up to engines, to be able to optimize fuels and engines for clean combustion. And so that's what this is my little bit here. From molecules to engines, we have, so I should say the Department of Energy put out a call for proposals. They received 261 proposals. They funded 46 proposals. We're the only one funded on combustion. And Ed Law, who unfortunately is not here, he's the director. He suckered me into being the co-director. And we don't yet know who the associate director will be. There are 15 people involved, including Fred and Yiguang Zhu, who's listed here. Yiguang's on the steering committee. Bill Green, I already introduced. There's people here from Sandia Combustion Research Facility, which is out in California, who are experts. And then also experts from other universities, as well as also someone from Argonne National Labs. And the idea is that all of us together are going to cover these areas of expertise, both theory and experiment, chemistry, flames in terms of the fluid dynamics, and also engine design. And so this is really nascent. The money is not here yet. Okay, so we're just starting to think about how to put this together, and we're all very excited about it. So, do I have a minute or not? Am I done? Should I be done? Okay, I'll just do this one slide then. So I hate it when people go over, and I don't want to be a hypocrite. So anyway, this is just one example of the kinds of things we do in terms of materials. So we are interested right now in the material tungsten, which is the prototype for one of the interior portions of this fusion reactor. And there are good reasons why one might want to use tungsten. You remember tungsten is actually what's the filament inside your light bulb, and it happens to be able to exist at very high temperatures. And that's a good thing. It has a high melting point. Also, it's a good neutron absorber. And the question that Princeton Plasma Physics Lab posed to me was, how easily does it incorporate hydrogen or its isotopes? Because it's going to get bombarded with those materials, and we're very concerned about that because hydrogen in metals often causes problems. Okay, it's an actor in corrosion, and so we've actually looked at this now, and we haven't actually looked at the problem of a neutron hitting metals, but we know that when neutrons hit metals, they knock atoms out of place. They form vacancies. Missing atoms are there. That's what this is supposed to mean. And it turns out that hydrogen loves those vacancies. They just go straight to the vacancies. And they live, many of them, that should have been an atom right there. And hydrogen, up to 6 hydrogen atoms can collect around those vacancies. And when you have that many hydrogen atoms, what we are able to do is calculate essentially what we call an embrittlement function. When you gather that much hydrogen together, it essentially makes the material crack and blister. And so we made some predictions about how likely that happens as a function of temperature, which could be very useful in trying to understand how to look to optimize a tungsten alloy that will inhibit hydrogen incorporation. We've already done that kind of thing for steel. So with that, I'm going to skip all the thermal barrier coating work and just say, and thank Don Johnson, whose work I had a chance to talk about. And Don is somewhere in this picture. Where is he? He's right there. Okay. And so with that, and so I should thank Princeton Plasma Physics Lab and also Princeton School of Engineering. They jointly funded this small project having to do with hydrogen and tungsten. So with that, I thank you for your attention.
Okay. Well, good afternoon. Figuring that I had 10 minutes, I figured I would focus on one example to tell you one specific aspect of our work on organic solar cells. Before I did that, I thought it was important for me to share with you some statistics. So I gathered this information. And so if you've seen this, bear with me for a couple moments here. So if you look at the global population stands at about 6.4 million people. And of those 6.4 million people, about 300 million reside in the United States. That makes it 5% of the global population. Now, if you ask the question of how much energy we consume, the global energy consumption stands at about 460 quadrillion BTUs. That's British thermal units. And quadrillion is 10 to the 15. Of those 460 quadrillion BTUs, about 100 quadrillion BTUs is being consumed in the United States. Okay? Those are all big numbers. So what do these big numbers mean? If you take these numbers, divide by the population, and then divide by the number of days there are in a year, and then divide by, let's say, the energy density of gasoline, what you get out is that the world consumes energy equivalent to 1.5 gallons of gasoline per person per day. And the United States then consume energy equivalent to 7.5 gallons of gasoline per person per day. So this is quite an alarmingly large number, considering that we probably don't even drink a gallon of water per person per day, okay? And from this number, you'd gather that, yeah, I mean, there is an imminent need for us to find renewable energy that is A, sustainable, B, has negligible impact on the environment. And that's why we look towards the sun. So I'm showing you here the spectral irradiance of the sun. Okay, the solar radiance is at 1 kilowatt per meter squared. And if you take those units, what this means is the annual sunlight gives energy at about 3.6 million quadrillion BTUs. If you do that same kind of analysis, what this means is if we can effectively and efficiently harness solar energy for an hour, that's enough to power human activity across the globe for an entire year. Hence, this motivation and this drive for solar energy and solar research. So solar cells are used to convert sunlight to electrical energy. First-gen solar cells are these single crystalline type silicon devices. The thermodynamic efficiency, so this is the maximum achievable efficiency that these devices can hit, is about 33%. In the lab, they've been demonstrated to be between 20 to 25%. Now, if you incorporate them as modules and you put them on roofs, their efficiency drops a little bit, so it's about 18%. The biggest problem with these first-generation solar cells is the cost. Okay? They're way too expensive compared to coal. So there's this next generation or second-generation solar cells. These are thin film devices, so they're polycrystalline. That drops the cost significantly, but here you take a hit in the efficiency as well. The materials that are used to make these thin film devices are cadmium, telluride, for example. They're rare earth metals. They could be toxic. And so we wanted to ask a different question. So I'm plotting here efficiency as a function of cost, reminding you that Gen 1 solar cells are right about here. Gen 2 solar cells are right here, so these are the thin film devices. Gen 3 devices we didn't talk about. These are the ones with fancier architecture, and so they're more expensive, but they're also more efficient. What the organic electronics community is asking is whether we can target right about there. We take a hit in efficiency, but we can dramatically lower costs. Indeed, market analysis that's been done has shown that if we can make about 10% efficient devices, we're in business, okay? So that's the question we want to ask. Just quickly, let me show you how an organic solar cell is built and how it works. So here you typically start out with a glass or a plastic substrate, okay? You have a transparent anode, and then you put down your organic layers. You need an organic electron donor, and you need an electron acceptor, and then you put on your cathode. So here are energy levels that are associated with the donor and the acceptor. So this is the LUMO level and the HOMO level, or the conduction band and the valence band. And so when you shine light, light gets absorbed in the donor, and then you generate an exciton. This is a tightly bound electron and hole pair. The electron then shifts to the LUMO level, and the hole remains in the HOMO level, and these get collected at the external electrodes. So solar cells are inherently not very efficient devices. Organic solar cells especially are not very efficient. The highest efficiency that's been reported a couple years ago is about 6%. Okay? And you can begin to understand why that is the case. The efficiency that's associated with a device is a compound of all these different efficiencies. So if you have one single step that's not efficient, that sort of propagates onwards. To characterize these devices, you plot the current density as a function of voltage, and you get a diode curve, and it's really the area here that's below the zero line that gives you how efficient your device is. The bigger the area, the better your devices are. Now, I'd like to call your attention back to how these devices are made. You'll notice that these devices are often built from the bottom up. Okay? You put down one layer, and then you put down the second layer, you put down the third layer. And that's because, I mean, we're following what's been established for the silicon industry. But organic is a completely different beast. They're frequently mechanically and chemically fragile. And so if you're using the same technologies to put down and pattern the cathode, for example, on the organic layers, you can potentially damage the organic layers. And so what we'd like to focus on is come up with non-invasive processing technologies to make these devices. So here in this example, I'm showing you how we can laminate to make organic devices. So the idea here is as follows. You want to make these devices separately, okay, the different components separately. And then in one final step, you bring them together. So in this example, we've basically patterned and deposited electrodes separate from the active layer. Here we're using polydimethylsiloxane. This is silicone. This has the same chemical structure as the RTV that you use to caulk your bathtub. You can pattern and deposit your electrodes without harming the photoactive layer. And then when you're ready, you laminate to make contact. Now, there are several merits associated with this lamination procedure. First of all, you have this modular construction of devices, so you can individually optimize the different layers. Second of all, you have custom engineering of the interfaces. So I've mentioned that charge extraction is a problem. You can imagine putting down chemical species here that can enhance charge extraction. And this is something that you can't easily do when you're building things from the bottom up. Finally, you can imagine doing this over large areas. And if you do this over a large area, it can potentially enhance fast throughput combinatorial testing of new materials. So we're working with a chemist right now who's going to synthesize a bunch of these new materials, and so we can inkjet print them down and laminate and test them really quickly combinatorially. So I wanted to show some data. So here are current density plotted against voltage for different contacts that we've made to the same photoactive layer. So we're putting down one contact, we're taking it off, we're putting down a second one, and then we're taking it off and we're putting down a third one. The point of this graph is to show you that this technique is actually really robust. It does not depend on the contact that you're making. What you're testing really is the characteristics of the photoactive layer. Now looking to the future, how scalable is this process? We believe this process is scalable and it's compatible to roll-to-roll processing. So these are processing technologies that have been developed and established for the newspaper industry, for magazines and whatnot. And if you take potato chip bags, for example, where they're depositing aluminum, and these are the specifications for depositing aluminum, if you use those specifications as a benchmark, you only really need about 100 machines to operate for a year to make 10% efficient solar cells. Now, of course, I'm not saying that organic solar is the way to go, but using the sun is clearly going to be one of the ways, and we think this is a good way to move forward. Oh. So just to show you that printing is possible, so these aren't solar cells, but these are sort of backplanes for displays that we've printed using sort of similar technologies.
I can use this. It's all right. It's okay. This is fine. This is fine. All right. As Greg said, I'm a senior venture officer with the New Jersey Economic Development Authority. I specialize in clean technology on the technology and life sciences team. We have a couple of people specializing in certain other areas, and since I came on board about 2 years ago, this was my specialty, and have been working to fund companies in this area and also create programs to address this segment of the industry. So for those who are not familiar with the Economic Development Authority, we're an independent state agency. We like to say that if the government shuts down, we're still operating because we're not under a line item budget. Oh, okay, fine. All right. These are the areas we cover: financing assistance, access to small business services, real estate development. For those who've driven along Route 1, if you've seen where Chubb Institute is, we actually own an incubator for life science companies. And recently, we actually took commerce into the Economic Development Agency, and so we have an international trade area, which is interesting because before where I was or have been focusing on New Jersey companies and attracting companies outside New Jersey to the state. I'm actually now meeting with a lot of international companies who are really interested in moving to New Jersey or investing in companies in New Jersey. So actually, Israel is very high among states, countries that are looking to invest in clean tech companies here, but also China. So those are the two countries I've been meeting with. So there is a life cycle of companies that we fund, and a lot of people become confused as far as what does the Economic Development Agency do versus other state agencies. So this is a little chart that actually put together this morning just to kind of show the progression. There's the New Jersey Commission on Science and Technology, and that really funds very basic research and development projects. As you move along the curve, we have an Edison Innovation Suite of programs. Those are the programs that I represent. And the reason why we have a specialized team is our partners are primarily the venture capital firms, the angel investors, there's equity funds. And so these are the companies that are startups primarily. They don't have revenues, there's losses. And they really require a specialized team and specialized type of financing. Versus the more traditional mature companies, and there's a group at the Economic Development Agency, and those are the traditional companies and where they look for 2-year profitable history. You can imagine that those are the companies that really partner with our commercial banks. So we like to say that we have financing that goes from the very, very early prototype stage, and then we move forward to very advanced and larger companies. But we are there to support the technology industry, especially clean technology. And the focus here is really what we're doing to really support that in the state. And so there's a New Jersey Energy Master Plan. It was released in October 2008. It's supposed to be updated every 3 years. I think it was quite a long time before this one came out. But it does list a series of goals, and that provides a blueprint for our programs that we are creating in order to support these goals. And the goals are listed there, and you can see we're looking to achieve 30% of the state's electricity needs from renewable sources by 2020. And in order to do that, we have to really be much more aggressive in rolling out programs to really service this community, and that's what we're doing now. The last bullet point is important only because the investing in innovative clean energy technologies and businesses is really the focus of what the Economic Development Agency is doing at this time, because we really take that policy and we implement it in action. And so, as you can see, these are some of the goals of the Energy Master Plan and how it affects the Economic Development Agency, because our role is really to expand the current suite of programs that when I looked at it 2 years ago when I came in, and I thought this really doesn't address the needs of the clean tech community, because the maximum that any one clean tech company could get would be $1 million, and $1 million doesn't go a long way for a lot of capital expenditures. And so I spent a lot of time looking at other states, calling companies in other states, and saying, what can we do to really bring New Jersey to the forefront and bring it to where it should be? So when people talk about California and how innovative it is, they're going to start talking about New Jersey. And I think we've done that, because about 3 weeks ago, the firm that is employed by the California Regulatory Commission called us, or actually called me, and said, I was reading about your programs and I think they're very innovative, and could you assist us in creating a solar incentive program for California? Which I then said that I work for New Jersey and I wasn't really ready to move, but it was a couple years ago. We probably would never have received that phone call. And so it's really encouraging that we are coming along the curve. And so where is this funding coming from? It definitely can't come from the Economic Development Agency, because like many of the banking functions, we've been impacted by companies that are not paying us back on our regular amortization schedules, and we've had to stretch repayments out, and therefore, as income goes down, we don't have as much money to support clean energy programs. So the question is where will we get them? The first program that's actually out there, the Clean Energy Manufacturing Fund program to support renewable energy manufacturers, is coming from the BPUs, the Board of Public Utilities, our regulator in the state, the Clean Energy Program Fund, and that's from the societal benefit charge that everyone pays into the local utilities. It then is funded into the Board of Public Utilities, and it's used to create energy efficiency and renewable energy programs. It's from that pot of funds that I created the Clean Energy Manufacturing Fund. But we have a couple of other pools that have come in. From the Regional Greenhouse Gas Initiative, which is the cooperative state effort that New Jersey is part of to cap our greenhouse gas emissions. We do have a pool of funding coming in for that, and it's about 30 to 35 million per year, and we are mandated to use that to roll out new programs. There's the Retail Margin Fund, which is legislation that was recently passed in March 2009 to support combined heat and power. And then there's the federal stimulus funds that everyone seems to be chasing. But in reality, our part of it that we're rolling out into programs is not a lot. It's only 15 million out of about 74 million that's allocated to New Jersey. And so I wanted to put this in perspective, and I just want to say that some of these went to our EDA board today, so it's really hot off the press, May 12th. And there's a 10-day waiting period for the governor to approve these programs. So until it's really officially approved, I can't go into all the details, but I can at least highlight for you what they are. The first one is the Edison Innovation Clean Energy Manufacturing Fund. Actually, that was approved last year. There's 24 million supported from the Board of Public Utilities for that. We had one solicitation already at the beginning of the year, and we've opened up another solicitation that as of June 1st. So within the month, the state will be announcing who the winners are of the first solicitation, but there's still quite a lot of funding available for the second one. So if you are a clean energy or energy efficiency manufacturer and you can meet what we call Class 1, according to the Board of Public Utilities, which is photovoltaics, wind, tidal, and some other technologies out there, then this is a pool of funding I would encourage you to apply for. The window actually ends July 14th for anyone in this room who's thinking of applying. The second one is, it's called Clean Energy Solutions Capital Investment Loan Grant Program. I'm not sure why everyone has to come up with these long names, because I think it's just a tongue twister, really, for the fact that these are funds that are coming from the Regional Greenhouse Gas Initiative to support end-use energy efficiency projects. And there's going to be about 36 million available. And this program is very important for companies to note, will be online as of Monday. And so therefore, and I'll go into the particulars, you'll see that 36 million is not going to be a lot, and it's a first come, first served type of program. So if you think that you may qualify, I would say check the website and apply as soon as possible. I can go through some of the particulars in a couple of the next slides. This other one was just approved this morning at the board, the Edison Innovation Projects Program. That's from the federal stimulus program funding. It's only $15 million. I say only 15 because each project can go up to 5 million. So there's not going to be a lot of funding for this, but it's going to cover the whole array of renewable energy, energy efficiency. It's going to be for biomass. It's going to be for energy storage. It could be for combined heat and power, and also alternative fuels. So I wanted to let you know that again, there's a 10-day waiting period, so I won't go through the whole highlights of this, but It's really primarily for those companies that have a proof of concept. It's not for the very early stage. And then the Research and Development Fund wraparound is something that accompanies the research and development grants that are available. There's 15 million available this year. And yeah, okay, 2 minutes. Wanted to mention that. And then there's the Combined Heat and Power Program. And then that's from our Retail Margin Fund. $60 million is available for this. And this will really launch us into some really massive waste to energy type of projects. This is the Clean Energy Manufacturing Fund. 3.3 million in grants and interest rate free loans are available for this. And as I said, the solicitation began June 1st. And then this is the program that it will be launched on Monday from the proceeds from the Cap and Trade program. And these are the categories of fund uses. So if you're installing equipment for combined heat and power for end-use energy efficiency projects, and that does include solar, state-of-the-art projects and innovative carbon emission abatement technologies, this would apply. I would mention that for any type of solar installations, they've modified it so that if this is a grant and zero interest rate program up to $5 million, but for those that are solar projects, because it's heavily incentivized, it's going to be loan only, and it could be repaid from solar renewable energy certificates. So these are the guidelines that will be introduced on the website on Monday. 1 million is the minimum, a very attractive interest rate. You're not going to get that in the private sector. And long repayment period, as you can see, up to 20 years. And the reason why I think this will go fast is because institutional is in there. So there's a lot of hospitals that want to do combined heat and power projects, among other type of entities. So this is the 866 number, but a lot of people know me in the room, and I have no problem sitting down, going through your requirements, and assisting you as you move forward. Thank you.
Okay, we're going to take a 10-minute. The industrial presentation will be one that's very close to my heart, Princeton Power Systems, which was founded in the year 2001 by 3 Princeton University graduates. So Princeton Power is a real product of the university here. So to start it off, both Darren Hamill and Marshall Cohen will give the presentation.
Thanks, Greg. And thanks, Pablo, for inviting us here and setting all of this up. As Greg mentioned, I graduated from Princeton in 2001, and we started the company in a dorm room at Princeton. So I guess we were about 9 years too early for the Endlinger Center, but I think it would have helped us out a lot if it was here then. The company, we make power electronics devices. Power electronics are components that are used in a variety of energy applications, and they're not generally the sexy stuff that you see like the solar panels and wind turbines, but they're there in almost every energy application. So there's a whole lot of uses for them. We generally work on higher power systems. So on the low end, about 5 kilowatts. Our core product is 100 kilowatts, and we do everything up to multi-megawatt systems. So the company got started. We did primarily a lot of military work with the Navy and the Army on shipboard power distribution, a lot of industrial control, various uses for power electronic systems, and we started doing R&D on wind turbines and solar energy in about 2002, 2003. And we have a patented electric circuit technology that we use that's called AC Link, and I'll talk about some of the advantages of that technology later on. So we have a core product for the commercial market, and we manufacture in New Jersey. We're over on the Forrestal campus by the Plasma Physics Lab, and we do all of our manufacturing right there. These systems that are about the size of a refrigerator. And we also have a couple R&D programs that we're working on with the Department of Energy and a bunch of military programs to look at using new materials for those products. So we're constantly developing prototypes newer, smaller, better, faster systems, but we also manufacture commercially. One of the key benefits that our power electronics bring, which is really how we got our start in the military, is what we call clean power, which back then really meant low distortion, including low EMI, electromagnetic interference. And this is very important on Navy ships in particular, where they have a lot of electronics packed in a small area, and they need very clean power. If you start getting distortions in the power, it can mess up the digital equipment and sensitive instruments and things. So we started working on making clean power converters back then, really for the military. And it turns out when you want to connect renewable energy sources to the grid, it also requires very clean power. The utilities require that you don't mess up the grid, basically. So we had a lot of that technology that we brought from the military world into the commercial applications. The markets that we look at typically are large distributed generation, so anything from a small business like the roof of a Walmart all the way up to fields of solar panels or large wind turbines, offshore wind turbines, and then also hydropower, tidal power, some of the other less developed renewable energy sources. We've also done some work with the utilities on energy storage systems. Our same power electronics can be used to tie energy storage, electrical energy storage, up to the grid. And that can be used for a variety of things, load leveling, some of the things that were talked about earlier today. And we're also now looking at combining both of these things together. So renewable energy sources typically vary with the time of day or with different environmental factors. And there's a lot of benefits to tying energy storage up with distributed energy sources. And that's a lot of what we're looking at now, are developing projects that are combining those things. Some of the rebates and subsidies and tariff structures don't work very well with this kind of system, but in the long term, we think it's the right way to go. It ends up supporting the grid in the best way possible, so I think that's the way the market's going to develop. And again, I'll talk a little bit more about some of the military work we did that led to this technology. Won't go into any of these details, but these are a lot of the reasons why our technology, the AC Link technology, is an improvement over power electronics as they existed before we started making these. And these advantages are different in different applications, but in general, they allow us to make devices that are more efficient, smaller, and more flexible than typical power electronics. So the core product that we manufacture now is a 100 kilowatt system, which is, again, roughly the size of a small business or a Walmart, Home Depot, in terms of the power level that it can support. And it's very flexible. That's one of the main advantages of it. We can use a variety of input sources, from solar arrays, wind turbines, or battery banks. And on the output, we can connect to the utility grid. We can sell power back to the grid, what they call net metering. We can also create microgrids. So if the utility power goes out, we can directly power building loads off of batteries, off of solar arrays. And we can do that dynamically. So when we get a signal from the utility or from some outside controller to cut off from the grid and establish a microgrid, we can do that, which is a pretty unique feature of this product. In addition to that, our commercial product, we're doing a bunch of research on a variety of new products. One of the biggest that we have now is part of a DOE program, which is called CEGIS, Solar Energy Grid Integration Systems, which is a fancy way of saying inverters. And we look at our system that we're developing as kind of a front end to the smart grid. So you can tie in, first of all, communications from the utility or from building management systems, and tie into a variety of variable loads where you can control critical loads, discharge energy storage to match time of use pricing, things like that. And this is a product that's in development now. In addition, we're working with some material sciences to get the improvements in the power electronics beyond what we have now. And one of the big ones we're looking at is silicon carbide semiconductors. We have two programs, one with the Navy that's been funding a lot of this work, and one with the Department of Energy. And the big target we're working on for the Navy is 98% efficiency and a power density of 3.3 megawatts per cubic meter, which is drastically smaller. Right now they're about 1 megawatt per cubic meter, and their next generation target was 2 megawatts per cubic meter. and we gave them a design at 3.3. So that's why they're funding this program. And actually, we're working on that closely with Rutgers Silicon Carbide Lab. Again, if the Endlinger Center was here before, maybe we would be working with them. For the Army, we've been working on microgrid applications. The Army generates most of their electricity using diesel generators out in Iraq or Afghanistan, out in the field. And the cost, when you take into account all the logistics of bringing the fuel out there, it's about $90 per gallon for a gallon of diesel. And this was a couple years ago. So they'd like to do anything they can to reduce fuel use, and that includes generating power with solar energy, wind turbines, also using batteries and energy storage to better manage power, basically. And so we have a program where we're putting power converters in front of a lot of the loads and generators to help them do that, basically to reduce fuel use. But this is applicable to the commercial world also. There's a movement in many places in the country and in other countries to establish microgrids where you can generate your own power, self-sustaining, tie in different types of resources to the grid without some kind of centralized controller. So what we're really working on at first is developing this system. Then eventually it's getting rid of that central controller so you can tie all these sources in, including electric vehicles and any new source that comes along tied into the grid. Finally, to close, we have actually done one research project with the university. A couple of years ago, we installed the first photovoltaic solar array on the engineering building. It was a 6 kilowatt solar array comparing two types of solar panel technologies and developing the power electronics to tie those in to a battery charging system. And then with the university, we were developing some advanced maximum power point tracking, basically control algorithms for the solar arrays. So we've had a great experience working with the university so far, and we have a bunch of different research programs that I think would tie in very well to what the Endlinger Center is doing. And then most importantly, we do research, but we're a commercial company. We want to manufacture things, sell things. We have a good customer network, and I think we could really help get technologies out of the university and into the real world. And that's my presentation. Thank you.
Don't forget, we're moving at a pretty fast clip here, so we're going to utilize the break and the reception for questions and better interaction. The next presentation is Alan Bruce from Sunlight Photonics.
Thank you, Greg. Well, good afternoon. It's a pleasure to be here, and thank you to the organizers for arranging this. It's a very worthwhile experience, and I think it's going to be great going forward. And thank you for the opportunity to give our brief overview of our company here. I'm Alan Bruce. I'm a vice president at the Sunlight Photonics. And just to summarize, we've been in operation since 2007. We're headquartered in South Plainfield, which is not too far from here. Our focus is we're developing and going through to manufacturing of high-efficiency, low-cost PV solar cells. And this has been a long-standing objective in the industry, but it's fair to say I think it's largely unfulfilled at this point, which gives the opportunity for businesses and new ideas. We believe we're bringing some differentiating technology here in terms of thin-film multi-junction. And we've also been very active in filing IP, which includes materials, cells, systems, and also into the distributed power generation, which would resonate perhaps with the last speaker. We're currently in a development and prototyping phase. We're well advanced and close to bringing first prototypes to the public and seeing how well we do in the industry. In terms of capabilities, our team, many from Bell Labs, experienced in materials, physics, optics, and many aspects that bring together and provide strength in this area. We have a fully equipped clean room facility in South Plainfield, class 100 to 1,000, and we can do complete processing there. What I would also say is we currently do have collaborations with several universities and also government labs. So we feel it's a good model for accelerating and bringing extra strengths to the field. Where our focus is, you know, if you look at what's in the industry right now, obviously silicon's the installed technology, and cadmium telluride, amorphous silicon are certainly current thin film technologies. And there's multi-junction technologies in terms of 3-5 monolithic from Spectral Labs and also MCOR. We're looking really at next generation, which we believe can include thin film multi-junction based on CIGS, copper, indium, gallium selenide cells. But our technology and our IP also has a broader application, perhaps into the current thin film SIGs at companies like NanoSolar that we saw highlighted earlier, and also the future generation of you know, polymers and others. So we've got a broader application base than the special focus. In terms of our TFM approach, what we're looking at is bringing together several advantages. One is to implement you know, more optimized individual absorber layers and individual cells to bring the high efficiency and manufacturability. Also to bring in a multi-junction some novel designs which can take advantage of the multi-junction in actually a hybrid approach rather than a monolithic approach, where, you know, again, as the earlier speaker, lamination can play a really good role in terms of bringing together, you know, different levels of absorption and efficiency and resulting in a net gain in terms of performance. It also provides the opportunity for flexible and stretchable substrates. And they're different. Stretchable is really a distinct field from flexible, and you know, has many applications across you know, government as well as commercial. In another set of words, what we're really trying to do is combine two sets of, you know, leading advantages in the field. One is, you know, the idea of multi-junction, where you have a stack of cells that segment the solar spectrum and bring the best efficiency out of each segment. And also thin films, which is really right now providing an approach for inexpensive fabrication of solar cells, but perhaps not the efficiency, whereas the multi-junction can bring the efficiency but not the cost advantages. So really we're bringing together those two sets of advantages in what we believe is a good winning solution. Just highlighting, you know, very briefly some things. You know, our materials work. We are able at this point to make very good SIGS type materials, which are dense, uniform, large area compatible, already in good crystalline form at low temperatures. And this opens up the range of substrate which can be used, including polymers, polyimides, and such. In terms of this is actually modeling of what the advantage of a 3-junction as opposed to single junction. You can get close to about 30% efficiency with currently achievable you know, performance in single cells, and if you have the you know, the support medium between the junctions to be at least 90% transparent, which is well doable in terms of currently available materials. Another point I'd like to highlight, I mentioned earlier about the spectrally adaptive, and what this really comes down to is if you look at you know, solar emission in terms of direct sunlight and diffuse sunlight, clouds, or reflected light, there is a strong difference in the spectrum, including a shift in the you know, about 100 nanometers between red and blue. What this means, you know, in terms, and this is specifically for multi-junction, you know, the monolithic 3-5 approach is typically you know, a current match configuration, and it's actually set for, you know, perhaps an optimum or an average illumination condition. And what happens is illustrated here. If you look on the actually the left-hand side here, you know, it might be optimized for direct sunlight. And then when you get diffuse sunlight, the efficiency can drop in about half. And that's something that you often don't hear about, but is accepted, you know, if you talk to the people in the area. With our designs, what happens is really you play to the maximum performance of all the cells under all illumination. So really, you don't lose the efficiency you would if you get you know, the differences in light. That also extends to differences in temperature and other performance conditions. Well, the types of product we're targeting, you know, of the order of, we believe 25–30% efficiency at, you know, essentially EN 1.5, which is terrestrial illumination. And the point here is that, you know, the high efficiencies you usually hear about are typically on half a centimeter square cell. You know, you're really looking to bring that up to larger area in terms of a good manufactured product. And the result is a higher power, smaller footprint solution without any concentrators. And also because of our designs, the highest performance at variable light. Selectable form factor comes from the use of flexible and stretchable substrates. And the SIGS material itself has been shown to be very robust, including in space conditions. As I come towards the end, what I'd also like to emphasize is, you know, we have a focus in terms of the cells and modules. Our technology really is focusing on multi-junction, you know, going up the, but it also extends into the single junction range. And while we're also looking at SIGS as the preferential material, the IP we have in terms of filings extends into the other ranges too. So we feel we have got a broad base that might be applicable, including into the polymer regime that we heard about earlier, you know, looking to the future as well as to the present. You know, some areas we're certainly open to collaboration. As I emphasized earlier, we work with several universities and government labs. But in terms of materials, there's always room to optimize the absorbers or the contacts or the transparent conductive oxides or others, and also bring advanced processing solutions which can you know, bring advantage of lower cost and higher performance. Components, you know, if you look at any multi-junction, usually the performance is often driven by the top cell, which is a wide bandgap cell, and again, any improvements that can be brought there through modeling, design, or processing will be you know, an advantage throughout the industry. And because of our multi-stack, obviously transparency between the different cells is a good solution. I mentioned briefly that, you know, we also have interest in IP and you know, collaborations and beyond just the cells and modules, including distributed power generation and control. And also we're looking at microgrid solutions, obviously coming from the solar side, but up through the control of the system. And with that, just let me thank you for your listening, and look forward to some good collaborations perhaps in the future with you.
Thank you. Okay, next is Adam Cohn, Princeton Plaza Physics Lab.
Okay, you already introduced me, but I want to leave this up to remind people of one thing. We're actually Princeton. We probably should be in the first category. We're not comfortable. Okay. Okay, so I'm Adam Cohn. I'm the Director of Operations for the lab. What is PPPL? We're a DOE national lab. We're one of the 17 across the complex. We focus largely on fusion and plasma science at this lab, but we also support the energy missions of the department as a whole. We are a science laboratory. If those of you who work with DOE know what that means. So we work with the other science organizations to do pioneering research. This really is next generation, long term. We're trying to develop the next generation for base load. That's the whole idea of fusion. And we also have a role in educating the next generation of scientists and engineers because, as I said, fusion is a long-term goal. How do you get people to engage in this type of research when you're talking about something that might be available 20 plus years out? What is fusion? Fusion, you take two isotopes, two nuclei rather, and you bring them together at very high heat. They fuse into something that's unstable. They break apart into an alpha particle and a fast neutron. Gives you huge energy multiplication. You take the alpha particle energy, you feed it back, that gives you the heat, so it's self-heating. You take the neutron, you hit some lithium targets, and you create more tritium, so this gives you the breeding to create more fuel, so you can keep this thing going. And out comes energy. It's all quite simple, right? So why fusion? Why are we even interested in this before I get to what the lab does? First of all, there is an abundant amount of fuel. Seawater has all kinds of deuterium. There's lithium all over the place. So this is a huge long-term future for how we're going to meet the energy needs. Environmental advantages, this is no carbon emissions, no greenhouse gases. There are radioactive isotopes that come from it, but they're short-lived, so you don't need a geologic repository. This is safe. It's got a very small amount of fuel. There's no runaway reactions or meltdown. There's no issues with nuclear materials proliferation. It's concentrated relative to solar. You don't need a huge amount of land usage. It's not subject to these daily, seasonal, or regional weather variations. But the one thing I will emphasize is this fits into a balanced energy portfolio. This is not supposed to take the place of solar, wind, and the others. This is just part of the larger mix. There are two approaches to fusion. There's a magnetic confinement and there's inertial confinement. As everybody knows, fusion is what powers the stars. How do you create a star on the Earth? Well, these are the two ways. This lab works on the top way, and that is you take a plasma, which is one way to get to these very high temperatures. Plasma has electronic properties, and so you can combine it with a magnetic field, and that's how you get to these really high temperatures. You use the magnetic field to drive the temperature and to confine this plasma. The other way, you probably heard in the news over the last, I don't know, several weeks or so, Lawrence Livermore just started up the largest laser facility ever. So this is a $3.5 billion facility that has 192 lasers, I think, and each one is the largest, most powerful laser in the world. So they have 192 of them. The whole idea of that is to do what's shown in this bottom cartoon here, and that is to focus the energy on a very small particle to create fusion. So that's the inertial confinement. We don't do that. We do the magnetic confinement at this lab. There are several ways to confine this. Anybody has seen the tokamaks or the eater? You create this donut and you have this toroidal fields and colloidal fields, and you confine the plasma and you keep driving the current to get to these temperatures, and eventually you'll get to the fusion of these isotopes, or these nuclei rather. There are some problems with that, and that's why we're building the ITER experiment in France, and we are very much engaged in that. There are some other concepts, and those are the ones that we really work on at this lab. One is something called the spherical torus. It's kind of a misnomer because it's not a sphere and it's not a torus. It's sort of a combination of the two. But if you look at it from afar, it kind of looks like a sphere with a hole drilled in the middle, and that's the name. The advantage of this is that it gives you high fusion power at low magnetic fields. And then we also work on something called the stellarator. It's kind of like a strange configuration, and wait till I show you the magnets, and you'll even emphasize that message. The advantage to this is we think this is the way eventually that we'll get to a power reactor, because it has passive stability and it allows the steady state operation. The plasma thinks this is steady state. We look at it, it looks kind of crazy. And so we're combining what we're going to learn from the ITER and the technology that we're developing, as well as other labs are developing, to get to practical fusion energy. We are committed to the success of ITER. I just show this to remind people that we are very much engaged in this international community. ITER is a huge thing. This is a guy or a person. It's a huge device that they're building. And so we're very much engaged in a number of aspects. Ours are working on things related to the fabrication of the diagnostics. How are you going to use this thing as an experiment? And we're also looking at plasma material interface, which I believe one of the earlier speakers mentioned. At the lab, we run something called the National Spherical Torus Experiment. I mentioned this is one of the alternative concepts for looking at how we're going to develop a power reactor. So this is a little bit smaller in scale, and that's what I mentioned. The spherical torus allows you to get a much higher power density for the same type of magnets. And so this shows what the device looks like. That shows it installed with lots of stuff around it, because again, this is an experiment. We're trying to get as much information out of it. But a power reactor wouldn't look much different. There'd be lots of secondary systems surrounding it as well. And this is a collaborative research effort, 50 PPPL researchers, but we also have 140 some collaborators, including lots of international. I mentioned the stellarator concept. This was the other experiment that we were planning to run. Right now it's in a state that's, well, it's somewhere in between having the funding to finish it and having this desire to want to see the next generation plasma device. So I mentioned this is kind of a crazy configuration. The way you get that is you create these magnets, which also look kind of odd in shape, and then you contain it into a vacuum chamber that's shown on the right. But this is what it really looks like. And this actually exists. We have these components, and we're ready to put them together. We just need to convince the DOE that this is worth continuing the project or restarting the project. But you can see the magnets in the crazy shape, and you can see the vacuum chamber on the inside. There are 3 vacuum chambers, and they would fit together, and then there are 6 magnet segments. I point this out for one reason, to show you that we're working on this. The other is this illustrates the outstanding engineering that is done at the lab, in this area. The tolerance to shift and twist this vacuum chamber into the magnets is on the order of plus or minus 5 millimeters. So we had to do this in air, and these are fairly large components. This is about the size of a person. So this is a very, very great engineering feat that was done at this lab. We're also involved in other scientific aspects of fusion, including the high-performance computing simulation program. Emily mentioned some of this earlier. And then we also look at applications of plasma itself. And this involves several activities. One is innovative fusion concepts, and that is looking at how do you really convert this idea into an energy source. We're looking at things like using liquid lithium. We're looking at basic plasma physics to understand how plasma applies to other areas, such as astrophysics and non-neutral plasmas. And this is, again, very basic science, but we are looking at engineering and applications, and this includes things like plasma rocket thrusters, which we're running experiments at the lab. We're looking at applications of plasma for materials processing. We're also looking at materials issues related to creating and developing fusion reactors. So this just shows another experiment that's run at the lab. I mentioned the lithium. The idea here is that we can coat the wall with lithium as a liquid, and that might prevent some of the plasma material interface issues that we're concerned about. And then lastly, we're involved in lots of communication and outreach. We are the lead lab for fusion energy for the Department of Energy, and so as a result, we are involved in communicating the idea of why fusion is important, sort of keeping the torch burning, and talking to all kinds of stakeholders, whether it's the public or Congress or staff or others, and try to get people to understand why we want to continue this research. You know, there are people here who have been dedicating their lives to pushing this forward, and thankfully, because we've made great progress, and hopefully if you look at things like the energy supply and demand curves, you will see that energy demand is not decreasing, and even if we hope to meet the current demands with the existing technologies or the near term, anybody can see that as we continue to increase the demand, we're going to need this type of technology long term to meet the future demand. So that's why we want to keep working on this type of technology. And the challenge that we have near term is to continue to expand plasma and fusion science collaborations within the local areas, excuse me, especially with Princeton, the School of Engineering, and the astrophysical sciences. So in summary, we've made great progress in fusion. We're not there yet. This is not a reactor that's going to be built anytime in the near future, but 20, 30 years out, we should see a demonstration, and then it'll be up to the economics as to whether you actually build these things after that. Yes, we can produce electricity in our lifetime. And for more information, I would encourage you to come visit. We are right across from Route 1, so pretty close. We have a shuttle that goes between the university and the campus. And so it's pretty easily accessible, and we're always open to visitors and showing off our wares. Thank you.
All right, next is Shihab Karan from Petra Solar.
Good afternoon. I'm going to be talking about Petrosolar, probably with less focus on the technical content, but you'll see from the presentation that we have a lot of vertical areas for research and development that I look forward to discussing with you later on today. We at Petrosolar have developed electronics and software and solutions that enable a single panel solar system. And what we mean by that is that today PV modules tend to be strung together in an array, and at the end of the array you'll find a device that's a centralized inverter, and then you have a solar system. What we have worked on for the last 3 years is enable electronics to go on the back of an individual solar panel, and thus your system is modular at the single panel level. Those individual panels can be put together in a large array and also can be used at a single level point. Obviously, both systems have many applications out there. You need the larger type of arrays, with the high voltage systems, and you need the modular, flexible ones. But you'll be surprised that you can go to utility applications with the singular ones, and you can go to residential with the larger ones. So the market exists for both. We at Petrosolar took this concept, or this product, to an end application. And that application is a utility application where we thought, okay, now a single panel can work by itself. Where can we apply it in a meaningful way? And we have approached companies in the utility space and thought, what do you think of putting the solar panel on utility poles? This got a lot of attention from utility partners, and we got together and perfected the product. And today, Petrosolar is engaged with no less than 20 utilities in the US and several others overseas for the commercial deployment of utility scale. When we say utility scale, it's many, many megawatts of those panels on utility poles or light poles. There's more than meets the eye here, and I'll talk about that in a second. These solar systems develop as smart grid systems as well. And what do I mean by that? Each panel has a communication system embedded in the electronics. And those actually vary from power line communication to wireless communication. And they talk to each other, they go to an aggregator, and they go back through a backhaul, for example, in the utility application, back to the central monitoring and command and control. There's also a host of functionalities that go with this, from sensing the grid to injection of reactive power, nonlinear power. By the way, they can work in the daytime, pulling the power from the sun, but they can also work at night because they're grid connected. And you've got an electronic device. You basically have a computer, an energy source, battery or capacitor, and a communication link all together. And this is IP based. If you read stimulus language coming out of Washington, anything smart grid related has to be IP based. This is IP based, which means it's compatible with other smart grid solutions. Just to show you that on the electronic side, we have what's called a grid tie inverter among other functions that we deploy. And at Petrosolar, we have probably about 20 patents that are exclusively either licensed into the company or we have filed for. We have a strong team working on digital control. We do power electronics. We do power semiconductors. We do communications. And what I would like to show here is the areas of R&D focus that we have and that we can work on together, either with companies from the industry or with the university. I put them in kind of three areas. There's solar energy conversion, and that covers power electronics and controls. And our particular focus is on digital control. We have smart grid, and with smart grid, again, there are electronics, communication, software. And the third area is the system integration. Basically, we put a complete solution out there to be deployed and delivered to our customers. So we are a designer, we are a developer, and we are a manufacturer of the end solution. and we have to interface to many other applications out there. If I look at the microinverter area of R&D, and I dig a little bit deeper, on the power electronics we do develop and manufacture DC-DC converters, DC to AC, inverters, the controls, DSP, content, and then there's a whole area when it comes to utility applications in regard to thermal design, in terms of failure analysis, in terms of physics-based failure, rather than just, say, looking at a RELX simulation of the lifetime of the product. And then a whole host of communication solutions that we have to deploy. We have what we call the second generation microinverter that we refer to as nanoinverter. And the nanoinverter is semiconductor based. It's a much higher level of semiconductor integration. With the electronics one, it's discrete components that you put on a board. With nanoinverters, it's literally having the full solution on a chip, either in a monolithic way or as an MCM, which is multi-chip module. This is just a way to look at the nanoinverters. And why nanoinverters are important to us, it's because instead of having a building block that, say, manages power out of a 200-watt panel, these would be about 15 to 20 watts each. So if you're using organic solar cells, or if you're using any thin film technology, now you can have what's referred to in the NEC code as an AC module that would work with smaller building blocks. And we really have to, just like looking at an iPhone that condenses everything in a small form factor, we have to do this at a chip level. In the smart grid area, that's where we truly have a lot of disciplines into one area. And I couple the smart grid and system integration here. But I heard today, or talking about battery storage. So our customers are saying, well, how much energy can you store in this distributed fashion? Can you fill that hole? I mean, in the pole application, can you fill that hole with batteries? It's an asset that's out there. We also have several cities that are looking at sensing technologies for, be it homeland security related or environmental related. Want to know, as you deploy those in neighborhoods and everywhere, we want to have, as you deploy them, we want to have hundreds of thousands of sensors so we can monitor air quality or monitor, against any terrorist attacks and know exactly, have an early warning systems. So the fact that we have a business model that combines, technological breakthroughs together allows for the deployment. Someone's going to go up there on a pole while he or she are up there. You might be able to deploy a host of technologies that reduce the ROI. I think that's it. I wanted to be brief and to the point. I think that's my last slide. So I'm not going to go through all of them, but it covers the disciplines that we are working on today, and we look forward to working with all of you. Thank you.
Finally, certainly last but not least, Joseph Forline, PSE&G. No? All right, surprise. Okay, we have 4 more presentations. Let me throw it out to you. Would you like to take a 10-minute break now, or go through the presentation and then we'll have the reception? Go ahead. All right. Oh, all right. Yeah, there's a couple hanging out here. All right, then why don't we start off, Imran Buddha, Innovative Engineering, will give his presentation.
Good afternoon, everyone. My name is Imran Gupta. As Greg said, I'm the founder and president of Innovation Engineering. We're a company located in Mount Laurel, New Jersey. We're about roughly have half an hour, 40 minutes drive from Princeton. I basically put the presentation focused on the renewable market. But I will talk a little bit more about looking and listening to you guys. There is a little bit more that we do, so I'll add some more comments into it. We design power systems that go into the manufacturing equipment for semiconductor manufacturing, for solar panel manufacturing, and for industrial lasers. Within the solar panel market, we basically mostly deal with the thin film side, which is the amorphous or monocrystalline silicon. And there are a number of companies that do those type of equipment. We basically sell our products into companies that are actually making equipment with which people make solar panels. And there are a number of companies such as the Santa Clara, California-based Applied Materials. There's Oerlikon in Switzerland. There's Leibold Optics in Germany. And there are also local companies here in New Jersey, and one of them is in Lawrenceville, which is EPV. If you look at some of the things that people are doing in the solar panel manufacturing, is basically everyone is working on trying to reduce the cost of the solar panels. And some of the companies are going to larger and larger panel sizes. And you can see in some of these cases, the panel sizes are about 2.2 meter by 2.6 meter. This is about the size of your garage door. And as they go through making those panels, I mean, there's a lot of technical issues, other things that come up, and I'll talk a little bit about what we add into it. And then when you look at an actual solar fab, this is just one particular company that makes it. There are a number of other companies that do it, similar things, but you see a number of these systems stacked up to make a fab that puts out 40, 50 megawatts of solar panels a year. We deal with two ends of this market also. While we help in the manufacturing side of the solar panel, we also work with some utilities in looking at or designing the large utility scale grid connected solar power plants or solar farms that they're called. And we can look at the cost of or impact of the cost of the solar panels on one end and see and really appreciate it when we are trying to reduce the cost on the other side. If you look at a typical large scale grid connected solar power plant, you see that almost half, more than half, the cost of the power plant is in the solar panels. And if you are able to reduce that cost of that solar panel, you have the biggest advantage that you can drop the cost of not only the capital investment of that installation, but also ultimately the utility cost of the power that's produced. In rough terms, if you are able to get the solar panel cost down by 20%, you can get the installation cost down by 10, 11%, and you can get the utility cost, the electricity cost down by about 10%. Another way to look at it is that if you take some of the installation costs today, one of the biggest hurdles today in this market is that because solar installations are very capital intensive, to get the cost down is key to actually be able to put more solar installations in the market. Today, if an optimized system would run somewhere around somewhere between $4 and $4.50 per watt peak, of which almost half or more than half is just the cost of the solar panel itself. If we were to implement, we work on some technologies which actually reduce the cost of solar panels. If we were to implement our technology with that existing cost structure, we can bring it down to between $3.50 to $4 a watt. In addition, many of the companies themselves are working on other ways to reduce that cost, which is either improving the uptime, yield, looking at lower cost of the material or optimizing their manufacturing operations. And that combined with some of our technology can really bring that cost down to roughly about $3 a watt. And that's a significant advantage for solar PV installations. So what we do, there's a process in the in the solar panel manufacturing where you take whatever this material is, whether it's a glass material or a stainless steel roll-to-roll type of material, and you deposit your silicon material or thin film on it. And that process is called chemical vapor deposition, and it's facilitated with plasma, so it's called plasma enhanced chemical vapor deposition process. Today it's done at one particular frequency, which is the most common frequency that's used today is somewhere around here, about 13 megahertz. But there's a lot of research that has been done in the last decade or more that shows that, you know, if you are able to increase that frequency, that you can really increase the deposition rate, which means that you can bring the time it takes to deposit the material down, or you can bring the manufacturing cost of the solar panels down. The other advantages are obviously if you are able to decrease the time down, manufacturing time down, you can have more panels that come out. So a fab that is putting out 50, 55 megawatts can put out 80, 90 megawatts of panels per year. All of this works very well on small dimensions. But as I mentioned before, many of the companies are going towards larger and larger panels. So as you move toward larger panels, the VHF doesn't work as well because the frequencies now are comparable to the size of your panels themselves. So the challenge is to solve that problem and get to something which has good deposition rate and good film uniformity. What I show over here is we developed some technology which allows us to reduce the non-uniformity on these solar panels. What you see on the left side is what is typically used today, which is a 13 megahertz, and this is the surface potential on one of the electrodes. This is about 2 meter by 2 meter, and this is, you know, RF cycles going up and down. If we take that same design and now put VHF frequency into it, all of a sudden you see that, you know, it's no longer a smooth potential. There's all these superposition of waves. You get all these standing waves on the surface, and it really negates the advantage that you would get from higher deposition rate. What we do in there is that we take the same, this is the same stuff that was running on the previous slide. We take that same application, same technology, and now we implement it with one of our technology, which basically smooths out the surface potential on this large area. And you can see that we can make a significant impact on improving the uniformity of this surface potential, and consequently we can allow these companies which are using larger panels to reduce the cost. We can allow them to use VHF to even further reduce their cost of the solar panels themselves. As I said, you know, I basically geared it towards renewable stuff, but as I said, we do more than that. If I look at, you know, what type of collaborations, and these are just some things that I threw together, there's definitely a lot more than just these. We can collaborate on grants or contract opportunities both on the state and federal level. There are a number of organizations, either state and federal, like DOE or Commission of Science and Technology. We also can work with the universities to optimize our technology, which is we can enhance our simulation capabilities. We have certain capabilities which are built in-house, but we do need to enhance them with adding plasma simulations and other type of things in there. We can leverage your existing lab equipment, or we can partner, or we can bring in equipment with our commercial partners. Today we do sell commercial products into the semiconductor market. We sell it into other markets also. The same application, I mentioned it as applicable to solar panels, but the solar panels, many of these technologies really came out of the flat panel display market. So there is a reverse application that you can take these and you can apply it into the flat panel market. You can also apply them to other areas that you see. In addition to this, we, as I said, we work on with 1 minute. No, I'm basically done. We work with RF power systems, which are used in many industrial applications. So whether it's trying to get, and I saw one of the gentlemen earlier on mention it, trying to get shale oil or oil from shale. There are applications where people use RF technologies. There's also if you are looking at capturing or reducing NOx and SOx from combustion type of applications, people use non-thermal plasmas using these type of products that we make to basically decompose NOx and SOx. This is basically all I had, but I believe that it gave you some idea of what we do, and we look forward to working with you guys.
All right, the next presentation is a bit of a shock, and you'll understand what I mean after I present Dave Kalakaitis from Power Survey Corporation.
Good afternoon, and thanks for giving me this chance to present here. I'm Dave Kalakaitis from Power Survey Company. We're located in Kearney, New Jersey, and we do detection of contact voltage in electric distribution systems. So we are a utility services provider. We provide services to utility companies. So let me give you a little feel for who Power Survey is and what we do. Our core business is electric hazard detection and mitigation services for public utilities. We do have a technology R&D component. We use our own proprietary technology in our work, and we always look to advance that technology. Formed in 2004 at Sarnoff Corporation, we're a spinoff of Sarnoff, and now an independent of Sarnoff. Since then, as we were acquired by GHO Ventures and the New Jersey Tech Council in April of 2007. We are widely considered the world's foremost expert on the subject of contact voltage, and I'll tell you more about what that's all about. We're responsible for the detection of more contact voltage hazards than any other group of organizations on the earth combined. We do quite a bit of work in New York City and other cities, and the result of our work has reduced public shock in New York City by 95% in 2 years. Leading U.S. and Canadian utilities rely on Power Survey as an independent expert in this field. So what is contact or stray voltage? You may or may not have heard these terms. Stray voltage, as it's often termed by the public media and industry, is neither a new problem nor specific to any utility or region. It's more correctly defined as contact voltage, and it's basically a fault in an electrical system. It's an unintentional connection between a power distribution system and a publicly accessible surface. These are shock hazards in the street, things you can step on, manhole covers, lamp poles, things you can touch, things you can get a shock from in the public landscape. And they result from breakdowns in the distribution system, which is buried underground. Contact voltage is present in all systems we have visited to date, and we've been to most of the major cities in the U.S. and many in Europe and Canada. And it has been responsible for injury and death in many cases. So it is a real problem in the public landscape. Of course, the concerns are public safety. It's a hazard to the general public, both human and animal. Dogs have been killed, people have been killed, so it is a real hazard. There's also a reliability component to this. Many contact voltage hazards are the manifestation of larger underground reliability problems. These are breakdowns in the system. They can result from collapsed ducts, burned out services, system decay, degradation, construction damage, digging in areas where there's buried wires can cause problems and so forth. Where do we find contact voltage predominantly? Well, most commonly found in areas where there's large underground electric distribution systems, and these tend to be in inner cities. There are some also underground residential distribution systems out there that have exhibited problems. And it's basically anywhere where buried infrastructure exists. Densely populated areas increase the potential for electrocution. Of course, where there's heavy foot traffic, people moving about, coming in close proximity to the electrical system, that increases the probability that a shock can occur. And contact voltage is not just found in cold northern cities. We found significant problems in warmer, newer cities, cities in Florida and so forth. Some children were killed not too long ago in Miami, coming in contact with a puddle that was energized by a street lamp. That's an indirect contact scenario. So it's pretty much available anywhere you look for it. And that's what we do. We look for it. A little bit about how we do that. Our proprietary technology is pretty much carried around in a pickup truck. If you look here, you'll see there's an electric field sensor located on the back of the truck. This electric field sensor is looking for 60 hertz energy. It's coupled to a digital signal processing system located in the back of the truck. There's video cameras and GPS antennas associated with the system, which allows us to track our progress and also to allow the user to associate the peaks in E field that the detector will find with a visual representation of where it happens to be located. The truck travels at about 20 miles an hour, so you can imagine as this drives by an energized street lamp or something, we can't stop instantly. It takes 50 feet or 100 feet to pull the truck over. The equipment that's in the truck allows us to go back and look at that peak in E field, compare the audible alarms that we get, the visual cues that we see on the screen from the video cameras, and synchronize that up, and that allows our crews to then go back to that location on foot, literally get out of the truck, walk back to that exact site, and walk around with some handheld instruments and really isolate the energized structure. So you can imagine this crew would be operating the truck. They would get an alarm from the system. They'd stop the truck, get out with some handheld probes and voltmeters, and really isolate that structure and cone and tape that structure off and report it to the utility. So it's really a search mission, a survey mission, where we go out in the city streets and move about until we locate these structures and then turn them over to the utilities for repair. What does it look like? Well, it's part of the landscape. So here's a few examples. This is a mailbox we found with 33 volts in Brooklyn. It was caused by a burned out service leg underground. And you can imagine a metal mailbox. Someone can walk up, grab that at any point in time. And, it's a handle you can get your hand on. And you can imagine that could give you quite a shock. 108 volts found on a street lamp along a beach. A problem with the neutral conductor in the light. And you can imagine, someone stops to lean against the pole and can receive a shock from that. 60 volts found on a sidewalk and front lawn. Again, buried infrastructure here. There was a problem with the service underground, causing the handrail and the sidewalk to be energized. So you may see occasionally in the news dogs being killed, people being shocked, and so forth. This is from the buried infrastructure that's decayed over time. Our research interests, of course, sensors, electric field sensors. We do have some interest in infrared imaging. We've done some work in steam leak detection also, which parallels our contact voltage detection in that it can be performed from a vehicle moving about the streets where steam infrastructure is buried. We're very interested in digital signal processing. It's core to our technology to isolate this 60 hertz signal we're looking for in a very noisy environment. Also distribution systems, electric distribution systems, power systems. We're interested in modeling those systems. You have to imagine that a lot of these leaks in the electrical systems are losses. These are energy losses and wastes of energy. And to the extent that if we could model that better and understand the quantity of energy that was being lost, we might have another avenue to convince utilities that this is a powerful technology to reduce operating expenses too. And of course, other elements of system modeling that might allow us to predict where failures might be prevalent and so forth are interesting. That's about it.
All right. Thanks, Dave. Okay, next up is Alan Delahoy from EPV Solar.
Let's see, do I need a microphone or anything?
No, it's all set up.
Okay. Good afternoon, ladies and gentlemen. It's really a pleasure to be here today to tell you a bit about EPV Solar and what we hope to develop, the next generation thin film photovoltaic modules. You'll notice we have two locations. We have a location in Lawrenceville where we have an R&D center and a larger manufacturing plant in Robbinsville. Okay, outline of the talk. Tell you a bit about the company, how we contribute in a practical way to energy production, a glimpse of our manufacturing, what our product looks like, what our next generation product will look like, what our technology requirements will be, and some ideas for desirable industry academic collaborations. So profile. We're in the area of photovoltaics. Our objective is to deliver solar electricity at the lowest possible price per kilowatt hour and with a shorter energy payback time than conventional wafer-based modules. So our company designs, manufactures, and markets thin film, amorphous silicon PV modules. We're one of the world's lowest cost producers. We're working on other aspects of systems integration and mounting. We do R&D in thin film technologies related to PV. We have novel large area deposition of active semiconductors and transparent conductors. We do device R&D. We also do our own equipment development, so we don't buy equipment on the outside market. We custom design the deposition systems that we need. The table at the bottom there is an overview of our manufacturing plants. Just down the road in Lawrenceville, we make 40-watt modules in a plant that has a capacity of 5 megawatts per year. In our newer building in Robbinsville, as you can see, our glass size is a bit larger. We have product up to 57 watts, capacity of 20 megawatts per year. And recently we've constructed a manufacturing plant which we own in Senftenberg, Germany, just north of Dresden, a capacity of 30 megawatts per year. There have been 4 talks previously that have given you some introduction to photovoltaics. So here you see it in real application. This is a 102 kilowatt power plant in Portugal, made with our modules, EPV modules. Each of these array sections, these big blue squares, has an area of 120 square meters, and you can see they're composed of solar modules, each about 0.8 square meters in size. So this represents the scale of what we're doing. You can see some of the numbers, the film thicknesses, and so on. Some of the layers are 10 nanometers in thickness, maybe 50 angstrom, 50 atom diameters, if you like, and roughnesses of 40 nanometers. So we are controlling properties on that scale, but then we go out and we coat acres of land with modules. Okay. We also make building integrated products. You can see some semi-transparent modules integrated into the Microsoft School of the Future in Philadelphia on the left there, and also called Solar Rail in New York City, balconies with semi-transparent modules on the front. So different kinds of products. This is a glimpse of our manufacturing. These are the plasma-enhanced chemical vapor deposition chambers that we use to grow the amorphous silicon, starting with silane as the input gas. We do batch coating. So in one of these chambers, we load 64 pieces of glass and we coat 60 square meters in a single run. The manufacturing plant in Germany has 6 chambers and with 5 megawatts per year capacity. This is a bird's eye view of the plant. So it's come a long way. In my experience, worked on little tiny solar cells at Brookhaven National Labs in 1980, all of which shorted and looked disastrous, but now we can manufacture in beautiful gleaming factories like this using those technologies that we've worked on so long ago. Okay. The left-hand slide is a picture of the solar cell. You can see the vertical stripes. Each of those long stripes is one solar cell akin to the crystalline wafer in the conventional panel. And on the right, you see the cross-sectional structure of the actual device. So we go to the larger area. Small, looking through the thickness of the device, you can see at the bottom the transparent conducting oxide. It's not a planar surface, it's deliberately textured. You can see P, I, and N layers and another set of P, I, and N layers. And controlling these morphologies and layers is of extreme interest to us. On an intermediate scale, you see the way the interconnects are done. There are no wires. You cannot have an open-circuited thin-film module because the contacts are distributed across a line. So you can see here the, anyone have a laser pointer?
The front of that is always, no, the one in your hand, the topmost button.
The top button? Oh, yeah. Okay. So the active part of the solar cell is here. You can see the 3 layers, 2 contact layers on either side of the active semiconductor. Over here you see the back contact of this cell coming down and touching the front contact of the next cell. And these lines are put in by laser scribing. Okay. Now, what is the next generation product? How is that going to be different? We're going to build on the amorphous silicon technology that I just described. Hydrogenated amorphous silicon. The hydrogen is in there to passivate defects. And we're now going to make a hybrid module with nanocrystalline silicon. And the motivation for putting in nanocrystalline silicon is that it has a lower band gap and hence is responsive in the infrared portion of the spectrum. This gold trace here is the photon flux from the sun. You can see there are plenty of photons out in the infrared. Amorphous silicon, this is the response of amorphous silicon, cut off at about 700 nanometers. If you add nanocrystalline silicon in the bottom stack of the tandem, now you can extend your response out into the infrared. So this new type of hybrid module, many companies are working on. Earlicon just had a press release a few days ago, got a new record, 11% module with this configuration. A lot of money being spent around the world on this, and lots of really tough problems to solve. So we need the high performance, transparent conductor, amorphous silicons, and other layers, intermediate reflectors, and nanocrystals. sorts of things we are working on. Yeah, so as I said, the main, if I break it down into the two main things that we need nanocrystalline silicon. We need an optimally textured zinc oxide transparent conductor. We need to be able to make those things over large areas, square meters at least. We're going to need some assistance in modeling, and hopefully we could integrate some newer technology methods into this traditional PECVD vacuum deposition, microcontact printing, osmonics. Now, what are the challenges? Nanocrystalline silicon is a rather tricky material. If you're depositing thin films from silane, you have a complicated phase diagram. You can have a stable amorphous phase, a protocrystalline phase, a mixed phase amorphous with microcrystalline, single phase microcrystalline. And it turns out you want to work just in this mixed phase region. That's where you get the best solar cells. It requires a completely different system architecture for these PECVD machines. Zimran already gave an introduction. We need VHF deposition. We need clever feeding of the power to the electrodes to achieve potential uniformity. So there are many technical challenges to be solved. So that's in the active semiconductor. Now, you also need the transparent conductor on the front. You need an electrode that is, the front contact has to be conducting, but it has to be transparent at the same time, and it also has to be textured to induce light trapping in the device. So at the moment we use commercially made tin oxide, but it has these drawbacks. And we've developed a new route for making textured zinc oxide by a method we call reactive environment hollow cathode sputtering. These, I'll show you what that is in a minute. This is a SEM micrograph of these films. They are not planar, they're very heavily textured. Our zinc oxide is more heavily textured than commercial tin oxide. Even with amorphous silicon, you get better results when you use our zinc oxide. So this is the principle of hollow cathode sputtering. Two facing targets, you sputter off the atoms and carry the atoms with the working gas to deposit on the substrate. For an oxide or a nitride, you introduce the reactive gas in the afterglow. We've made these different materials. This is what the textured tin oxide looks like. You can see plain glass here looking through this piece of glass onto the table. It's beginning to look milky here with tin oxide. And with our textured zinc oxide, you can see it's a very hazy appearance. We're not just doing square centimeters, we're doing square feet here. Some other areas that may be applicable, microcontact printing could be applicable to developing these textures for TCOs, plasmonics. We would like to apply to increase light coupling or absorption in the active layers. Just winding up then. So what do we see for industry, academic collaboration? I've listed some very specific topics here, and also listing our vision for how how the Andlinger Center can interact with New Jersey companies and utilities involved in PV, and some other concrete suggestions here. Conclusions you can look at. Thank you.
Thank you very much. Our final speaker is Kevin Duffy of Novita.
Oh. I want to thank you, Greg, for having me, and thank everybody for sticking around for the whole thing. It's a pleasure to be here. There's a lot of really interesting and cool stuff that I'm hearing about, and I hope a lot of it is going to come to fruition in the next few years and make our world a better place. But until we have cheap fusion energy, or until Craig figures out how to trap lightning bolts and store the energy, we all need to become a lot more efficient. There's a lot of waste in this planet of ours, and humans waste a lot, especially when it comes to powering buildings. So Novata Technologies is a way to help reduce waste in a couple different ways. Most of us probably know that buildings are the #1 emissions of CO2 in the world. 12% of our water use, almost 40% of our CO2 emissions, 65% of garbage, and 71% of electrical consumption from our buildings. So how, why, what, where do we start? Where do we start to make it more efficient? Well, our cars have dashboards, and they tell us, how fast we're going. They give us vital information. They're designed to give us that information as efficiently as possible in a quick glimpse when we look at them. So that way we can keep our eyes on the road when we're driving down the road pretty fast. What about our buildings? How are they working? What about a dashboard for our buildings? That's what most of them have. Oh yeah, here it is. It's down in the basement, hidden somewhere, and it's definitely collecting real-time information for itself. Utility bills, the old standard of figuring out how much energy you've used in your building, give you historical data 30 to 45 days after the fact. And this is what they look like. And they're pretty hard to figure out. And accounts payable gets these most of the time. Building engineers and facility managers, they never see this stuff. They have no idea what their building's working, and that's, for most of them, is just good enough. So this is a new way. This is a building dashboard. This is a Novata energy flow monitor. And it gives you real-time information of how much electricity is coming in from the grid, how much gas is coming in from the gas main. It can also tell you what you're producing if you have a renewable energy source attached to it. So why real-time energy monitoring and visualization? Energy efficiency, how do we get it and how do we keep it? It's one thing to do an energy audit and make your systems more efficient, but what happens when that guy walks out of the door? Do you lose that? Do the systems sort of creep back to where they were before? So it's energy efficiency, it's energy awareness of building occupants. If you show people what's going on in a building, you really, it has a cultural effect. I know in my building that if I walk out of my office and I don't turn off a light, somebody will literally, the next person who walks by sees I'm not in there, will turn off a light. Our computers, we unplug them at night, the power strips we unplug. It all makes a big difference after you add it all up over a year or whatever. So education, buildings as learning tools. The more buildings you have hooked up and being able to see real-time energy information, the more you can learn about human activity, especially in places like Princeton University. If you had buildings all hooked up, it's quite a science study. And show off. A lot of our clients are big corporations and banks and stuff that are saying, we have this whole new initiative to reduce our energy consumption. How do they display that to the world? So energy efficiency, real-time energy information enables you to take corrective action in time. Make adjustments, see the results in real time, and don't slip, make sure the efficiencies last. One of our case studies is Liberty Science Center, which is a 300,000 square foot science museum in Jersey City, New Jersey. They got our system in July of 2008 and have since been able to reduce their energy consumption by 40%, a little bit over 40% now, with no capital improvements. It's all operations and maintenance stuff. They really learned a lot about their building. They have 3 full-time staff on hand, building engineers, and they just didn't know. They have a very sophisticated building management system, which only tells them what they programmed it to tell them. So nothing was watching the building management system. So this is one of the things that they didn't see in the building management system, and that was a good chunk of it right off the bat. You can see their decline. If I look at 365 days, everything converted into BTUs. There's my number, 41.1% reduction. And here's their cost of doing nothing in the bottom right-hand corner. So that's how much money they've saved against their baseline in basically 11 months. It's kept them in business. And there it is, 40%, $500,000. So energy awareness for building occupants. A lot of our clients have kiosks when you walk into their lobbies and stuff. They're touch screens. You can go through several different screens to take a look at things like carbon footprint. You know, our goal at Noveda is to roll up everything into one dial that gives you context and meaning to the raw data that goes into it. That quick dashboard, you know, look down, see how fast you're going so you don't run off the road. Education. Buildings can become living laboratories. You know, they're a good way to start programs for STEP and STEM, and also to teach about sustainability. We are in the process of getting hooked up to all 83 Newark public schools, which will all have kiosks in them as well. And we're in probably about 60% of them so far. And the kids are already starting to compete, schools against each other. They're learning about, you know, what it is, you know, our generation, past generations really never, you know, saw. It's pretty spectacular stuff. It's just a, you know, one more way of showing how you can, there's our carbon footprint screen. Show off to the world. You know, corporations and government agencies and stuff are spending a ton of money on renewable energies and more efficient systems. And, you know, solar PV is beautiful, and when you go up to the roof and look at it, it's pretty cool, but it is up on the roof and most people never see it. So how do you bring it to life? How do you show it off to the world to show what you're doing? This is our sun flow monitor that shows real-time information. The sun goes over, it's basically a picture looking south. The sun actually moves in real time over the way the sun would move over. There's a paranometer hooked up to it, so it shows real cloud cover, rain or snow, whatever's happening real time. Shows all the pertinent information. It tells you how your system is producing. That's an important thing because with solar PV, once it's up there, you know, unless you're monitoring it, you have no idea what it's really doing for you. Some more screens that show how well the renewable energy system is performing. Obviously, this is geared toward New Jersey because it's showing, you know, New Jersey SRECs and how much you can generate. Again, back to the building management systems. They tell us lots of things about our building, mechanical systems, air quality, et cetera. What I've found in the 15 weeks I've been working for Noveda is that most of the buildings I go into have these very sophisticated building management systems, but none of them are hooked up to the meters, very few of them. Some of them are starting to, but they just are not looking at the actual flow of energy into buildings. So you have all this information, and they do a wonderful job at what they do, but they're not telling you that information in a way that you can then display to people who can understand it. A lot of building management systems are just configured wrong, and you get a lot of inefficiency out of, you know, misconfigured systems. So by being able to have something that looks after your BMS system on a, you know, a whole, you know, picture of the energy usage in a building, you can pretty much figure out whether your system is working efficiently or not. Again, data is, you know, critical to learning what we don't know, but data without context and meaning is just noise. So we try to reduce it, again, to one very simple way of saying, how am I doing? A quick way. From there, we can split down into different screens and different, to look at even the raw data if you wanted to. But roll it up into one thing, facility performance index. How well am I doing? How well is my building? Some of our clients have this dial for their entire enterprise level. So they can see, they have 100 buildings. They can see, you know, 100 buildings rolled up into one dial. They can then hit the dial and break down into subgroups, break down into individual buildings as well. This is 31 Tannery. This is my building, our building up in Branchburg, New Jersey. It's the first commercial net zero electric building in the United States. So over the course of the year, we produce more electricity with solar PV than we consume. We actually produce about a month's surplus. So we've modified some Priuses to plug into the building and actually get about 3 cents a mile on those Priuses and reduce our carbon footprint another 27%. How did we get there? Energy efficiency plus renewable energy plus the monitoring and visualization equals sustainable high-performance buildings. Because once they're there, you got to make sure they stay there. Just some of the systems in our building, high-efficiency systems. Perfect score of 100, on track for a 3rd year in a row, an Energy Star. We reduced our carbon footprint by 82%. And this shows how many acres of trees we'd have to plant to sequester the comparable amount of CO2, metric tons. And that's pretty much it.
Thank you. All right, that concludes the formal presentation. I'd like to invite you all to the next floor. We have a little reception, and then we can chat about what we've discussed today. So once again, thank you very much for coming.